Hello, this is the fifth video in the root series of OCR Pure Core AS Further Maths. It will connect the roots of equations topic with the complex numbers topic by looking at solving polynomials with complex roots. If you have not yet covered complex numbers, you may wish to do so before watching the rest of this videos. In the complex number sessions, we identified that quadratic equations had either two real roots, one repeated root, or two complex conjugate roots, i.e. a pair. You may want to pause here to remind yourself and relate this to the discriminant and sketch some graphs for each of these options for complex roots, real roots and repeated root. Moving on, you might want to stop and think about what can you deduce about the roots of any cubic equation? A cubic equation will have three roots. The options for this are three real roots, one real and one repeated real root, one repeated root as in repeated 3 times, or one real plus one complex conjugate pair. Let's have a look about what these might look like. Well, for three real roots, it'll be something like this, where you have 1, 2, 3 real roots. If you have a real and a repeated root, it might look something like that, where you have the repeated root and the real root. For one repeated root, for example y equals x cubed, you would have a very flat repeated root at the origin, for example, or transformed to one side or other. And finally, for one real and one complex conjugate root, you would have the turning point but not going through the axis, and then one real root. So you can see that for the roots of a cubic, you're going to always have at least one real root. On this slide, there are some graphs to better demonstrate that for quadratic, you can have one complex conjugate pair, and for the cubic, one complex conjugate pair with one real root. And for quartic, you can potentially have two complex conjugate pairs, or one complex conjugate pair, or none. So these are the key ideas. That complex roots occur in conjugate pairs for any polynomial with real coefficients. The factor theorem, that if f of alpha equals 0, then x minus alpha is a factor of f of x, and that fact that this also applies to polynomials with complex roots, and the previous work we've done in the relationship between our roots and the coefficients for polynomials. Do pause here and go and revise these ideas if you feel you need to. Let's look at a quadratic equation example where we know that we're going to have some complex roots. We know this in part because they've used the letter z rather than x in the equation, so it's az squared plus bz plus c equals 0. We're told there's one root equal to 3 plus 2i, and that a equals 1, and asked to find the values of b and c. There's more than one method for doing this. The first thing I hope you'll notice is that if we have one root equal to 3 plus 2i, the complex conjugate will be 3 minus 2i will also be a root. Let's use a method which looks at using the roots. The sum alpha plus beta will equal 3 plus 2i plus 3 minus 2i will equal 6. In other words, that's the minus b over a. Given that we know a is 1, b equals minus 6. If we look at the product, then again reminding ourselves that this is like the difference of two squares. But of course you add as I squared equals minus 1. That must equal C over A. And again that means that C equals 13 because A is 1. So we have therefore found B and C. Another method we could use is by expansion. So here we know we're using the factor theorem here. So that we have z minus 3 plus 2i multiplied by z minus 3 minus 2i. And here I'm going to use a little bit of a, not exactly a trick, but a rearrangement. So I'm going to move that so it's z minus 3 minus 2i and z minus 3 plus 2i. So all I've done there is just to move the brackets within the brackets. I haven't actually changed anything other than the brackets there. The reason I've done that is because then it's easier to see that it's, again, using the difference of two squares, z minus 3 squared plus 4, which is z squared minus 6z plus 9 plus 4, or gathering those terms together, z squared minus 6z plus 13. Again, that gives me exactly the same result. B equals minus 6 and C equals 13. So here we have a slide using, just to remind you, the method 1. And then also the second method using the factor theorem. Moving on to look at a cubic equation. Again, we know it's going to have complex roots because they've used the letter z. So z cubed plus 3z squared plus 12z plus 10 equals 0. They've told us one of the complex conjugate roots and they've asked us to find the other root. Well, I hope that immediately you realise that there's another root equal to minus 1 plus 3i. And then there will be one real root. Using the roots and coefficients, we can see that the sum of three roots, let's call them alpha, beta and gamma, but of course we know two of those roots already to be the complex conjugate pair. So all we're doing is adding those plus gamma, which gives us minus 2 plus gamma. But of course we know from our previous work that that is going to equal minus b over a. And in this particular example, a equals 1, b equals 3, c equals 12, and d equals 10 from this equation here. Therefore, we have that that is equal to minus 3. This leads to the conclusion that gamma, the real root, is minus 1. In the method 2, we'll do the same as we did before in terms of setting up the factors. So we'll have z minus minus 1 minus 3i, z minus that complex conjugate, and then let's call it z minus gamma for that third real root that we're looking for. Using that same way I did before of making those two become z plus 1, squared, plus 9. Then I'll be multiplying that by this z minus gamma. This leads to z squared plus 2z plus 10 times z minus gamma. Considering this, then by inspection I can see that minus 10 gamma must equal plus 10 by considering the units, the coefficients of the units, and therefore this tells me that gamma equals minus 1. That's the quick way of doing it. Of course, I could multiply out that quadratic z squared plus 2z plus 10 by z minus gamma and then compare the coefficients with the original equation. In this second example on cubic equations, I'm given an equation that z cubed minus 2z minus 4 has one root equal to 2, i.e. the real root, and I need to find the other roots. Now it's likely that these are a complex conjugate pair. There are various methods that I could use, such as algebraic division, expanding brackets, or comparison of coefficients by inspection. I think the comparison is the easiest and quickest method, especially when a equals 1, as it does in this case. Therefore, I'm going to say that as I know that z cubed minus 2z minus 4 equals z minus 2 times z squared plus some unknown b times z plus some unknown c, I can then compare and contrast the coefficients. So for example, for the units, I know that minus 4 must equal minus 2c, which would be what I'd get if I multiplied it out. Therefore, I can say that c equals 2. If I go on to then compare the coefficients for z, I can see that minus 2 on the left-hand side will be minus 2b plus c on the right-hand side. Now, I already know that c is 2, so therefore 2b will equal 2 plus 2 equal 4, and leaving me the answer that b equals 2. You may want to pause here and check all that working for yourselves. So if I now have that quadratic equation, which I know to be z squared plus 2z plus 2, if I want to find the complex conjugate roots, I can either guess them or I can use the quadratic equation, which will pretty quickly give me the complex conjugate roots of minus 1 plus or minus I. You can check this by multiplying out the factors if you want to. Similar methods can be applied for quartic equations, and you may want to go back and look at the options for the graphs. And think about the options for the 4 roots. If you're given one complex root, another can be stated at once, and then try that quick comparison method. If you are given 2 real roots, find the quadratic factor, and then use the comparison to find the other quadratic factor. Remember the trial and error method from GCSE. They're likely to be all integer real roots. If you are given a quadratic factor, then you can either try and factorise or use the quadratic equation on that, and then use the comparison method to find the other roots as quickly as possible. Comparison may sometimes be called inspection in some textbook. See the notes and examples in Integral or your textbook for examples of solving any quartic equations. That was the last video in the Roots of Equations series for OCR Pure Core AS Further Maths.